Hinge laws. In the last lecture, we learned about binary cross entropy laws, which is a loss function used for binary classification. Here, we are going to look into another loss function which is also used for binary classification, and it is called as hinge loss. So the next question is, what is it so special with hinge loss that makes it specifically useful? And the answer is, generally when you take a loss function, let us say you take BCE, binary cross entropy loss, what are you trying to do? You are trying to classify something into some particular class. Let us say you have class 1 and class 2, and for each input you want to classify it either to class 1 or to class 2. This is the task. What hinge loss does is, it makes a model not just be correct, but it should be confidently correct by a certain margin. This is the difference that hinge loss introduces. That is, it does not simply want the model to say that, okay, it is 1 or it is 2. Instead, it wants the model to confidently say that by this margin, I know that the answer is class 1. Or that by this margin, I know this particular example, it belongs to class 2. So this confidence margin, that is what hinge loss newly introduces. You can think of it like this. Let us say you are writing some multiple choice examination, maybe engineering entrance examination, and you have 4 choices, A, B, C and D. In some cases, when you're writing the exam, while you read the question and you do some calculations, you may have an intuition that, okay, probably it is option B, or maybe probably it is option C. But there will be some questions in which as soon as you see the question, you will be very confident that this question, surely the answer is B. So there is this difference that this confidence brings in. Sometimes you will be very confident that for this particular question, surely it is option B. By this particular margin, I know it is option B. Sometimes you may not be very sure, but you know that, okay, option B should be marked for this. That is the difference that hinge loss is talking about. So let us see what logic does hinge loss use so that it can predict by such a confident margin. This is what we are going to discuss in this lecture. First of all, I'll make you familiar with the terminology that we are going to use, whatever we are going to use in this lecture, and then we'll see how exactly hinge loss is working. First thing is X. X, as you all know, it is the input. In the last lecture also we used X. Whatever we call as X is the input. Next thing is Y. Y would be element of -1 or 1. That is, it can take only 2 values, either -1 or 1. And what is this? This is the true label. True label means when you are given any particular input X, what is the actual class that it belongs to? You have 2 classes. First class is called as 1 and the second class is called as -1. Which class does X actually belong to? That is called as Y. Okay. Next one is f of X. F of X, this is the model output. You have a model. To this model, you are going to pass X. X is what you are going to pass. Then you know the actual answer is Y. Y is the actual class it belongs to. But whatever the model is outputting, this is what you are going to call as f of X. You can call it f of X or Y cap. Both are the same stuff. In the last lecture, we used Y cap notation. Also, you can call f of X. Both are the same thing. Whatever is the model output, that is what we are calling as f of X. So, as of now, you understood that, okay, now the task is clear. You want f of X to be as close to Y as possible. This is the task. But one thing here is, this f of X is not going to be the class. That is, output of this model is not going to be 1 and -1. Then what is it going to be? This is what makes hinge loss special. One point you have to notice, when we were using binary cross entropy in the last lecture, what was the model output? Model was outputting the probability that this particular input x belongs to class 1. This is what in binary cross entropy the model was outputting. But in case of Hinge loss, you want the model to output a score. It is not probability, it is a score. So using this score, we will identify whether it belongs to class 1 or class 2. So keep in mind, last lecture when we were talking about binary cross entropy, the model was outputting probability. But here it is a score and it is not probability. Okay. You just need a score which you are calling as f of x. Now let us see how is this score helping us to classify either into class 1 or class 2 or class 1 or class minus 1. Okay. What I'll do first is I'll first write the equation and then the loss function, and after that we'll see what exactly is this loss function, how is this coming up, and what is the logic. Okay. As of now, just keep this in mind that the model is going to output a score which we are going to call as f of x. This is the loss function. L is the loss function. You have y and f of x. That is, loss function has to do something with y and f of x because you know y is the real label and f of x is what is the score that model is outputting. Your loss function looks like this. It should be max of 0 and 1 minus y into f of x. This is the simple loss function that is used for Hinge loss. Next question is, what is this y into f of x and what is this logic of having maximum of 0 and 1 minus y into f of x? We'll first understand y into f of x part. The term y into f of x, f of x, this term, this is what we are going to call as margin. What is the margin here? Margin is going to tell you how well the model agrees with the true label. Let us say you already know true label is 1 or minus 1. Let us say for this case true label is 1. Then y into f of x will tell you how well does your model agree that the true label, let us say model found out something, some f of x. Then how well does this finding agree with the true label? This is what y into f of x is going to tell you. Next question is, how is it agreeing, right? This is what I'll tell next. Let us say there are different possible values of y into f of x. Let us see each value and understand, depending on the value, how can you say that how much the model is agreeing with the true label? Okay. First case, what if y into f of x, if this is greater than 0, what does this mean? If it is greater than 0, that means prediction is correct. This is the first thing you have to understand. Whenever y into f of x is 0, greater than 0, that means prediction is correct. Similarly, if your y into f of x, this is lesser than 0, that means your prediction is wrong. This is the basic thing. So you would, as of now, you would feel like, okay, it is just classifying because whenever y into f of x is greater than 0, it is saying your prediction is correct. And whenever y into f of x is lesser than 0, it is saying your prediction is wrong. So till this point, you will feel like, okay, the model is simply saying that it is class 1 or class 2. Next thing is, one more logic that is going to be applied is, your target is not simply to make y into f of x greater than 0. If you do this, your prediction is correct. But in Hinge loss, your target is to make y into f of x always greater than or equal to 1. This is your target in Hinge loss. So this one that you are introducing, this is your confidence margin. If it is greater than 0, at that point itself, you know the classification is right. But Hinge loss, it specifically tells you that you always want y into f of x to be greater than or equal to 1. So this 1 is the margin you are keeping. Because of this margin, you can say that confidently my classification is right. This is what Hinge loss is newly introducing. And one more thing, how is this prediction right and this prediction wrong? So you can simply see it like this. Your classes are 1 and minus 1. So 1 is positive, minus 1 is negative. So if y into f of x has to be greater than 0, that means it has to be positive. What should happen? Whenever the true label is 1, your f of x, this should also be positive. Whenever your true label is minus 1, your f of x, this should be negative. Then y into f of x, that is minus 1 into f of x, will be positive. So if your model simply does this, that is, it outputs a positive value. I told you that your model should have an output. Okay, I'll just draw it once more. Let us say this is your model. You are giving x to the model. Then this output is f of x. If your model simply does this, that is, it gives a positive value whenever it is class 1. It gives a negative value whenever it is class minus 1. Then your classification is right. But what you want with hinge loss is, you want this y into f of x value to be greater than 1. That means your confidence will increase. Next question is, how are you going to enforce this, right? So basically you have to understand, even if your classification is correct, even as y into f of x is greater than 0, still your hinge loss is going to penalize. Even though you are correct, you are going to be penalized till the point you make sure that you are correct by a considerable margin. This is the logic. Next thing you have to understand is, we'll see how exactly we want the loss to be. Okay, I already told you, if it is not correct by a considerable margin, you will penalize. You will say loss is not 0. I am going to penalize you by some particular amount till the point you make sure you are correct by a particular margin. How we are going to implement this is, whenever if your y into f of x, if this value is greater than or equal to 1, then you know your prediction is correct, that is anywhere there. Plus what you are going to do is, you are going to say my loss is 0. Whenever the value of y into f of x is greater than or equal to 1, you know your prediction is correct, plus it is confidently correct. So what will you say? I will say, for this particular classification that the model has done, loss is 0. Model is perfectly right. What if it is lesser than 1? If this value, if this is 0 less than y into f of x less than 1, that means y into f of x is a value between 0 and 1. What does this mean? I already told you, if it is greater than 0, already the prediction is right. So here also the prediction is right, but you are going to add a loss which will be equal to 1 minus y into f of x, which means this y into f of x, you know it is a value between 0 and 1. So this would mean your value of loss, your loss value, this loss will be between 0 and 1. I'm not writing this there, it should not keep confusion. Okay, I'll mark it here. This would mean your loss value is between 0 and 1 in this particular case. So keep in mind, it is actually a correct prediction. When your y into f of x, the model output, whenever it is between 0 and 1, prediction is right, still you want to penalize. You are saying my loss will be equal to a value 1 minus y into f of x, which would mean there will be a loss of something between 0 and 1. Last case is, what if y into f of x, this value, if it is less than or equal to 0. So in this case, you are saying your prediction is wrong. Your prediction is wrong, so surely you have to penalize. How are you going to penalize? You are going to put the same loss function of 1 minus y into f of x. What would this mean? This would mean your loss is greater than 1. Why is this greater than 1? Because you know y into f of x is a negative value. So if you do 1 minus some negative value, it is going to be 1 plus that positive part, which would mean your loss is surely going to be greater than 1. That is when you are having wrong prediction, you are going to add a loss greater than 1. When you are having right prediction but is not confident enough, then you are going to have a loss which is less than 1. When you are having a right prediction which is confident, then your loss will be 0. This is the logic. Another way of expressing the same logic, whatever I have written here, another way of expressing the same logic is by saying that I want maximum of 0 and 1 minus y into f of x. So this is the loss function that I wrote in the beginning. This loss function, maximum of 0 and 1 minus y into f of x. That is same as what I have written here. If you see this, in this case 0 will be maximum because y into f of x is greater than 1. If you do 1 minus some value which is greater than 1, this will be a negative value, which means 0 will be the greater value and hence loss will be 0. In all other cases, your loss will be 1 minus y into f of x. So that is this particular loss function. One more thing is, you will not have just a single example. Instead, you may have n different examples and you want to find average loss. This is how you generally use. So how do you take average of this? You will do 1 by n into sigma I is equal to 1 to n. Max for each of these examples, what will you do? 0 or 1 minus, instead of y into f of x, for each of the example, it will be yi into f of xi. So what does yi and xi mean here? Xi means the ith input and yi is the ith output, right? Output means true label. Yi is the true label and f of xi is the output, xi is the input, okay? Xi is the input, f of xi is the output of the model, yi is the true label, right? So this is the scenario. This is the loss function that you have. One more important thing is, I told you that this particular loss function is called hinge loss. Have you thought in between this lecture why this is called as hinge loss? There should be some reason, but if you see whatever we have written till this point, there is no reason why this should be called a hinge loss. So why would it be called a hinge loss? Just think about this. I'll give you just 5 seconds to think. Just think, why would this be called a hinge loss? Okay. So the reason it is called as hinge loss is like this. If you graphically express it, if you try to draw a graph, then the hinge loss graph will somewhat look like this. This is 0. Let us say this is 1. This is 2, 3 and so on. And this axis will denote y into f of x. Okay. This is y into f of x. Then if this is the case, just think about this. You are giving different inputs and you are going to get different outputs, and this y into f of x value, it will take different values. Then how will this graph look like? I'll just draw the graph and try to see whether you are able to relate. Okay. I'm simply going to draw the graph. See if you can relate. So this is how the graph will look like. It will come here and from here it will be straight. This is how the graph is going to look like. Are you able to relate why the graph is going to look like this? The reason is, if you see the hinge loss formula here, there is a point, a particular point where y into f of x equal to 1, after which loss is 0. So if you see the graph, there is one particular point where y into f of x reaches 1, after which the loss is always 0. See, this one is loss, this axis is loss. So after this point 1, whatever be the value of y into f of x, it doesn't matter, 2, 3, 4, whatever be the value of loss is always 0. But before that, whatever be the value of y into f of x before that, be it 0, any negative value, whatever it be, it is linearly increasing towards the negative side, right? This is the case. So if you see this graph, at this point it forms a hinge. This is why it is called as hinge loss. At the point y into f of x equal to 1, it forms a hinge. This is the point. At that point exactly, it looks like a hinge. There is a hinge after which loss is totally 0. Till that point it is linearly decreasing. From the negative side it is linearly decreasing. It reaches the point y into f of x equal to 1. There it is like a hinge and suddenly it moves straight. It's all 0 after that. This is why it is called as hinge loss. Okay. So now you understood why it is called as hinge loss. It is a piecewise linear shape in which at y into f of x equal to 1, you have a hinge-like situation. Hence it is called as hinge loss. One more thing, because this is analysis of loss function, let us just write the gradient as well, because you may need gradient. So we'll cover that part as well. What is gradient? That will be dl by df of x. What will be the gradient of this particular function? If you see, there are two different cases. First case, if y into f of x is greater than 1. In this case, gradient is clearly 0. But what if y into f of x is less than 1? In that case, this particular function takes action. So the gradient is not 0. If you take the derivative of this with respect to f of x, what will be the situation? It will be minus y. This will be the gradient. So the gradient here are 0 if y into f of x is greater than 1 and minus y if y into f of x is less than 1. One point to note here is at y into f of x equal to 1, it is not smooth. So at that point, the function is not smooth. Clearly you can see here from the graph itself it is clear. So for y into f of x greater than 1, gradient is 0. Y into f of x less than 1, gradient is minus 1. So what did you understand from this lecture? First thing, you need to understand how is hinge loss different from other loss functions. Especially if you see cross entropy, binary cross entropy and all, those are probabilistic loss functions. But here hinge loss is more margin based loss function. Okay. And what does hinge loss do? Hinge loss ensures that the model doesn't just predict the right label, but also keeps a buffer zone. It says that there is a margin. If this is the border, then I am keeping this much as the margin, and after this point, this much is my confidence margin. So this buffer zone is the between the classes. This improves robustness of the model. So main point is hinge loss penalizes predictions that are wrong or insufficiently confident. Both these cases. If it is wrong, it will anyway penalize. Even if it is right, if it is insufficiently confident, still it would penalize this particular prediction. This is the most important point about hinge loss. So that is it about hinge loss. So next lecture, we'll move on to the next loss function.